I'm hitting record, and let's start. Okay, what questions do you guys have? We are recording now. Any questions you have? So if you get the mic on, ask about your day. Looking for
Was there like a meeting ID thing?
Yeah, the application has to be downloaded first, and then when you click the link, it'll just automatically.
I have a question. So, can you explain interactions?
Sure. Interactions. I'm going to might pull up some jump data for this. And I didn't go too hard. I really think what I put on the test for interactions is really what we went over in class. Because I might mute you, Josh, when because you don't have that much chatter in the background. But if you want to, I'm just muting you. But unmute yourself if you have a question. Just like anytime you have a question, just like unmute and be like, "Hey, what's up?" Because you can click the little audio thing down there to turn your mic back on. So just so like now everyone can hear me perfectly. So with interactions right here, what we have going on is the interaction of how when we change one X, it is going to change the impact of another X in the model. And okay, let me not show you guys R right now because I was working on the interaction question just a little while ago. I'm like looking at R right now. Let me open up a new thing. I don't want to delete off all my stuff. I could save it, but you'll see a good bit of R on the test. Okay. I feel bad. I'm not used to this silence. So an interaction plot is what we really want to understand and the grasp of what's going on right here. So let's look at an interaction plot. I don't like the way that they're basically scrunched in what you've seen in R. Like I haven't really liked the R's visualization of interaction plots. And let's see right here. I'm trying to find a really good interaction plot that I like. It's interesting. Let's go ahead and start sharing the screen right here. I got 500 million things up. I'm gonna make sure not to show you guys the test. So let's go to share screen, desktop. Okay. So I'm gonna write down interaction plots here to start. Interaction plots was the first question. So this interaction plot right here shows that someone's, we're trying to measure their attribution to self. And they're either going to rank it at what happened as an outcome or as a success or a failure. These aren't really quantitative measures. And usually, and I'll say this, a lot of times interaction models, usually an interaction model, we're first seeing them with quantitative variables, but usually in an interaction model, you see a categorical swap on the X because you really, it's best visualized that way. This is a crazy interaction plot right here. ACM, production sales. Let's just find a nice and easy one. Looks like, hey, this looks like some R interaction plots right here. I really want to find a nice and easy one. People hate, here we go. So the response. So they're changing levels of treatment A, and they're looking at, this is probably right here. Usually you do like a three-way, a low, a medium, and a high, and actually, truthfully, and this is actually good stuff because this is what we're going to get into. It looks like treatment A only had a low and a high level. Because if you add in, when you do design of experiment, if you add in a middle, this line can now bend and you can look to see if the relationship's linear if you're doing an interaction plot here. So they're trying to measure some sort of response with whatever this data is. So what they're doing is they're saying to themselves, how does treatment A change, the effect of treatment A when we change treatment B? Does everyone see how it's like, how does one variable change? Because going from low to high on A, what does that do to the response? Anyone can turn on their mic and talk. Feel free to just click the mic button and be like, I mean, what does it do to the response when we go from low to high on A? It's a complex question.
I don't understand what's the difference between treatment B and like related to all those lines.
This is, imagine this plot right here is something like we're looking at people's levels of anxiety. That's the response right here, okay? This is now a psychological experiment. So with the psychological experiment, people are reporting how much anxiety they have to us. Treatment A is whether or not they get therapy. So this is the no therapy group, and this is the therapy group. So with this in mind right here, treatment B is the medication level. So if you look at treatment B as the medication level, you have your low amount of medication, your high amount of medication, and your middle amount of medication. Does everyone understand how we're changing different variables? This is medication over here, and this is therapy. Does everyone understand this with the interactions right here? Does anyone get it? You get it? So here's the thing. Is if somebody is on, and I think this works out perfectly with what I came up with this, because think about this. If someone is on a low dose of medication, maybe this is a good response, like this is decreasing anxiety, let's say. If someone's on a low dose of medication, and then we increase their, we give them therapy, then all of a sudden the response goes up. But if someone's on a high dose of treatment, and we give them therapy, what happens to the response? What happens to the response if they're low here, and then we switch them to high, but they're on treatment B high? See how the response goes down? What's going to happen here depends how the response changes. Depends on one variable and the other variable. This is the pure idea of an interaction right here.
Mute your audio. Brian, there's 3 of us right next to each other in the library right now.
Oh, so no.
You're probably getting...
Yeah, we're getting like feedback. And oh, that's funny. All right, I want to go over, I see, I did, you guys are all online. Let's see if we can find a really good. Here's some of the big concepts with interaction plots. The big concepts with interaction plots are the idea of that the more they overlap, because let's find one that's not significant here. Look at some really interesting plots. This person had added some curvature. When you have one that's not significant, I wish we could get a really nice plot on here. I want to see a really nice, perfect residual plot showing no relationship. And this one's a little bit old versus new, and then rod hours. Who knows what that is? But if you notice, when is the slope bigger? When the rod hours is what?
When it's old?
When the rod hours is right here, the slope.
The whatever 50 is.
Yeah.
15 hours.
The line for 15 when it goes from old to new has a bigger slope. So when this variable is here, the slope from old to new, the effect of old to new is different. Do you see how this variable on the right is changing the effect of the variable down here? Because old to new is not always the increase that we see right here. This is the increase on 25, and then this is the increase on 15. So what you're saying is that what happens with one variable depends on the other variable. That is an interaction right there. They're interacting with each other. When we see one that is not significant, to show the counterexample, we should see non-significant interaction plots. And this one's good right here. No, it literally says no interaction on it. And if you see, if you're on this line right here, the change each time is the same. Like if you go red dot to red dot, as you change on this variable right here and change on this variable, you're not actually, there's no difference. It doesn't matter which line you follow. You see big interaction plots like this, and you can quickly note here where the strongest interactions are. Perpendicular lines are super strong interactions. Interactions are something, when you get a look for them, the concept is changing one variable will change how another variable acts. So I'm trying to think of a really good thing, like a good interaction with like studying, like something we talk about every day. But changing one variable will change how another variable acts. Let's see if we can find one more good one. Talk about. I do like this treatment one because it really shows like multiple interactions right here. Moreover, just interactions with multiple levels. Because treatment B, if you look, if I told you, does treatment A always increase the response? What would you tell me? What would you tell me? Does treatment A always increase the response? You would say it. You'd say what?
No.
You'd say no because it depends.
Depends on what the treatment is.
It depends on treatment B, right? Treatment A's effect depends on treatment B. Treatment B is the line you're following right here. So treatment A's effect depends on treatment B. And when you look at the formulas, like I literally want to show what I have on the test. When you look at the formula, you see that when you put in one variable, it's going to change the slope of another. If you go to homework 7, right? Let's pull up homework 7 here. Oh, look at this. Test 1 resave, test 1 new. What could that just open that right here? So I was working on that again, and that's all good fun and stuff. So let's not show that. Everyone's like, go check out the video. We showed the whole test. I think there's interactions on homework 7. Let's go down to that. And this, I'll post. Keith is posted for 6. Actually, just saw something that reminded me. I put in there. Looking at these interaction plots right here, which you guys can't get. I'm not going hard on interactions because you guys didn't really get them in the homework because of the problem in R. So I'm not killing you guys on it. It's probably gonna be like 4 or 5 points tops, like out of 200. You know, the strongest interactions are right here. We're seeing average temp and average humidity. I really want to see the variable on it. This is a little bit stronger. The p-values are going to show me where the interactions really are, but these are all the interactions. Things with the smallest interactions are going to have the most parallel lines, less parallel lines. And you see, even if you look at what it's doing here, it's not showing you every value. It's literally turning it into a categorical variable to do this. So it's doing average temp as a categorical, which is generally, we think of categorical levels for the interactions right here. We see the interaction term in. This is a very important thing right here. When we go to the equation, let's look at the equation, which is right down here in this question. I want you to take a look at this equation and understand it. Writing out this equation, when we put in it's bill size, bill times size. So when we put in size of 1, what we are doing is we're making a positive bill effect. Now, if you look at what bill normally is, do you see how bill is negative? Pretend bill is the number 54. Pretend size is 6. What does this solve out to right here? If size is 6, this solves out to point what bill? Just put in size of 6.
You guys get an audio lag too? Yeah, a little bit. But was bill 54?
Yes, 54, 0.54. Now, when you put this back into the model right here.
So, size 6?
Size of 6. And when you put that back into the model right here, you get 0.54 bill. And that's positive. If you substitute that in where this is, like if this was negative 0.54 bill, both of these terms would go away. Both of these terms would go away. Because what's happening is the effect of bill, it's a flat line now. There's no, bill is not doing anything. Do you guys see how it's changing the slope of bill? Do you see that? Do you see how it's changed the slope?
Kind of. It's.
What happens if size of party is 100? What happens to our model if size of party is 100? Just plug in 100 to size right here.
So, it's 9.
It's 9. And if it's 9, then all of a sudden this is a very positive term. And all of a sudden the effect of bill is huge, right? Because if you say size of party is going to change, you see how size of party changes what happens to bill. Also, bill, if you put in something for bill, will change what happens to size of party. You see that?
So, say it's still 9 for size of party. So,
it was 9?
Yeah.
That would make the effect of bill positive. So bill now becomes something that increases tip percentage. So this is saying, what this is saying is, what does that mean for the interaction? Parties that are bigger, this is saying, like, if a party is bigger, then the effect of bill will be a positive effect. Does that make sense? But if the party is smaller, the effect of bill will be a negative effect. Does that make sense? I think this is a great example right here. So let's listen to it one more time. If party size is really big, then the effect of bill...
Smaller than...
By about 6. It's like at 6 is when the line goes flat. Do you guys see this interaction term right here where as bill size increases, it's going to make this like substitute in 10, this will be 0.90 bill, right? You guys see that? So then if we put that over to this term right here, because all we're doing is solving the whole equation to make it just say something like this. If you put that over to here, what you will get is you will get a positive effect of bill. And that's the important thing right here. You guys see that, or?
Positive effect as in?
As in positive
effect as in it makes it.
It's literally the slope of bill going from negative to positive. All of a sudden now, for bigger parties, bill size will actually increase tip percentage. Does that make sense? Because when you tell me for a small party, if a party is small, what happens if we have a party size of 1? Then we add in this 0.09, and the effect of bill is actually negative. But with this in mind right here, when we have larger parties, the effect of bill can actually be positive. So you're telling me the effect of bill depends on party size because they interact with each other. And what you're seeing up here is if you see something like this with the interaction plots is, let's show one right here where something goes from negative to positive. It's often hard to find one like that. Oh, good. This is one right here where it goes negative, negative, and down here it's positive. So the effect of average temperature on demand will actually be, average temp will actually increase demand when the average effective wind temp is at its lowest. Does that make sense? If you look at this plot right here, when effective average temp is at its lowest, you see why I'm selecting this line right here? When effective average temp is at its lowest, the effect of average temp, because now I'm moving across this, right? Do you see how I'm moving across this line? Will actually increase demand. When effective average temp is at its maximum, right up here, the effect of average temp will actually decrease. If we were to put in that interaction term, then do you see it now? And if let's interpret this one real quick. Is this still average temp and effective average temp? That's why they look so small. Oh, okay, this is a good one right here because it's negative positive. When we look at average humidity at its minimum value, what happens to demand as average temperature increases? What happens to demand as average temperature increases when we look at average humidity? You guys might be seeing it. If we're looking at average humidity at its minimum value, which it says here average humidity min is the minimum value of average humidity, if we increase average temperature, demand's going to go up, right? But does that mean if we increase average temperature, it'll always go up? No, there's an interaction because you can barely see this line. But when average humidity is at its maximum, right down here, then increasing average temperature will actually decrease demand. And that's the interaction. It's like, well, if this variable's this, then the slope will actually, it'll change the slope. You're telling me the slope or the effect of it changes depending on what one variable is. Does that make sense why it's an interaction? Like, to tell me the impact of one variable, you have to tell me the impact of another variable. Yeah, like if I said, average temperature is high today, does that mean high demand? And you'd say, does that mean higher demand? And you'd have to say, well, what is the average humidity? And I'd say, oh, it's the average humidity is really low. And what would you tell me that average temperature is going to do what to demand? If the average humidity is low, what will average
increase?
It's going to increase. But if I tell you, oh, the average humidity is really high, what is average temperature going to do to demand? It's going to decrease it, right? If you see this line right here. And then if you think about it, if we have parallel lines...
Decrease.
I think we might be lagging time, but you guys are exactly right. If we have parallel lines, which we can't find a perfect example of, this one's a decent example of parallel lines right here. You see, let's ignore the bottom line, but do you see how it doesn't change the slope with these right here that much? The more perpendicular they are, the more of an interaction there is, because the more it's changing the variable. So the more parallel they are, the less interaction. More perpendicular, more interaction. More parallel, less interaction. Because then it stays the same. You know, when you change from one variable to another, it stays the same. It's like, well, it decreases by the same amount no matter what average humidity is, or whatever we're looking at here. No matter the average humidity, average wind speed will affect demand about the same way. I know we're ignoring that bottom line, pretending it's something. Do you have like a text? Can I help out with interaction?
So is there a value for this interaction effect?
Yes. Oh, yes. Is there a value? There is a coefficient.
Is there a value for this interaction effect?
Yes. Right here, we have in here an interaction p-value. Just the same thing. So here's a really good question. I'd like to give my So with this in mind, think about this. The lower the p-value, the more what the plot will be. When the p-value is really low, you'd expect the interaction plot to look like what?
More perpendicular.
Exactly. So yeah, when you see them really parallel, you're going to have high p-values because they're not significant. When they're really perpendicular, you're going to see a more significant interaction, lower p-values. And you could say higher coefficient, but you know, that's all standard error, coefficient, t-value stuff, which you can get small values and it still be significant. So p-value is universal. P-value is the standardized metric by which we measure significance. So you go to the model right here and you say, you know, if we look at the average temp, average wind speed, we can go look at this one right here, average temp, average wind speed. I think it's this one right here. I mean, that looks a little perpendicular, but you know, you look at the p-value and you say, it's not significant. That could happen by chance. So I would toss that out of my model. I think there's another interaction term on this page, and this one actually is significant. So if you were to plot this, and all these are calculated the same way with estimate divided by standard error, t-test, two-sample t-test. More questions if you guys got them. I mean, I'm sure you do, but...
Are you getting a lot of lag?
Yeah.
You guys getting a lot of lag? How bad's the lag? Is it like...
I think it's just because they're right next to each other.
Oh, okay.
I was sitting with them, and yeah.
I'm gonna move.
Can we talk about the check regression code and the 3 plots that it gives? So
that's great stuff.
Yeah, I'm pretty comfortable with looking at the scatter plots. Yeah. But the histograms, I feel like some of them, I feel like there's always something a little wrong with them. But we've said, you know, I don't know. Just can we give her the histograms and the QQ plots?
Yeah, no, that's I really like how I went over that on the test. I thought it was very true to what we've done in class. Believe me, you'll see things on your test. You're like, man, Brian just flat out asked that in class. So going to class and all that stuff's really good. Taking notes. So let's talk about the plots that we get. I'm trying to think. Man, I'm trying to think if I have a model up in R that I could. Do I not have it up? Okay, good. There's a little bit of data in the bottom of the screen that could be related to test stuff. Okay.
Is this that you have pulled up right now? Is this the solution to homework 7?
Yeah, it's homework 7 solution, which I'll probably post.
Can we look at the plot for this one?
Sure, yeah, definitely.
I was going to check regression for that.
Yep, it's up here, isn't it? Well, you couldn't run the check regression for it because it's a multiple regression, and he hasn't coded that apparently. I mean, he's coded everything. I actually disagree with the key on this.
Okay. Go ahead, sorry.
The plots on this one, like this plot right here is your main concern, because it's your residual model. And so when I look at this right here, this is what you got, right?
Yeah, that's what I got.
So when I look at this, if I were to, I always talk about in my office, I've got we drew out all these things on the board. I would circle this right here, and maybe circle this a little bit. That's about. If you think about what is making this not perfect, what is making this not perfect, maybe this blank area a little bit, and maybe this, but that's not freak out to me. I'm always overanalyzer. When I used to take tests on this stuff, I would overanalyze, but this little sparsity right here is probably due to a lack of data. I would say possible issue of heteroskedasticity, possible outlier. I would like to check the leverage on this one. I'd like to check the Cook-D on it. Like that's a concern to me at that point. I would say I need to check the Cook-D on that point. Possible heteroskedasticity. Want to take more investigation into that. And then that's about it. I'm not going to call this a nonlinear component, even though I do see a slight bend. I think it's a little overanalyzing, but that's my primary concerns with that. So I think it's a pretty decent.
Yeah, and then for the horsepower and top speed.
These actually, the individuals here, because the individuals, your primary concern is always going to be the multiple regression. The individuals are some concern, and what we do see here is kind of the class. I think we did bring this up in class. It's so good we're seeing this here in practice. When you have a lot of data at the start, more data means more scatter. And I got in trouble, I've mentioned this story a few times, I got in trouble mentioning on a test, oh, that's heteroskedasticity. Maybe. Because we only have a few points out here, and with few points comes little understanding of the standard deviation. So is it heteroskedasticity? Maybe, maybe not. I have a little bit of a concern, but we are seeing a spread out here on the residuals when we're using on that X. Down here about the same thing. You see how many points are in here? More points mean more scatter, and that's why you see the majority of the scatter. Because maybe if we had that many points out here, I would also say that our models are lacking a lot of data in the later portions. So that's something I noticed there. That on some of the X's we don't really. They're right. The X's are right skewed. Can you visualize the histogram these X's come from? Can anyone do that? I don't know. Maybe I just do too much stats.
Yeah.
Because I mean, the X's have a lot of values that are like centered here, and then they're spread out. So they're right. It's a right skew. It's probably like a right skew unimodal histogram. If you start throwing all those into bins, you make a histogram with it. So you need those conceptual things is what you slowly have to start thinking about. If you wanted to look at the normality of these residuals, you'd actually be flipping the plots. You see why you'd flip the plot to look at a histogram of the normality? And does this look like it's built up in the center and goes out evenly on the sides? And now it's a histogram like this, and not because this is a peak, but the density of the data within this spread. You just understand what I'm saying right here? I hate you, Zoom meeting. We'll immediately start back up the meeting if we get kicked. And I'm recording, right? Yeah, I did. I just hit the record button, hit the thing start. Do you see how I can see a histogram in this? Who does not? Who does?
Yes.
You do see it? And for anyone watching,
took it and flipped it to where it says residuals and poly.
Residuals would now be on the bottom, and it's not that this is the peak. This is not the peak.
There's a huge delay.
The peak is going to be because of the density of data. Like, if the data was all dense over here, and all dense over here would be a bimodal distribution, because you'd have a peak here and a peak here. It doesn't matter how high this goes, because you're no longer looking at, let me move that out of the way, you're looking at just a histogram. A histogram is a univariate collection of data. So when I visualize horsepower, I see that horsepower has a right skew because the density of data is over here, and then it skews to the right. When I visualize, it's not because of a shape like this, it's because of the density of data. When I view the histogram for residuals, I flip it in my head, and then I see all the data is really dense here in the center. I mean, you could just push all these points down, and it would still be a histogram with a peak in the center, even if those points were in flat. Does that make sense to everybody?
Yes.
Good deal. That's a good visualization to be able to do. Or good that you can see that within this data right here. So I don't see any primary concerns with this. Let's pull up another one that shows the traditional 3 images. I think we had one on 6. Let's go to 5. That's going to show simple linear. There we go. Okay, so this is excellent right here. I mean, this is violation galore. I start by looking at the values right here. All violations. Violation of linearity, violation of equal spread, acidity, and violation of normality. So you go through the linearity problem isn't as evident. maybe if we were to draw like this, the linearity problem is hard to draw on here, but it exists, and it's so small that I'm gonna accept that on faith, or rather, the evidence of it is so large, hence the p-value. P-value for the linearity is telling us, whoa, you got some nonlinear aspect to this model. Over here, I would say the non-normality most evident. I mean, that's a ridiculous violation. That's scary violation. Your residuals are all messed up. They don't follow, what the 68, 95, 99.7% rule says you have for a normal model. Equal spread. If you notice, the data is really dense here at the start. So that's where you would expect it to be the most spread out, right? If the data is dense, more data means more spread. But we have the reverse. We have over here at the end, when we have very little data, that it's all just spread out. So this is the reverse of when you can be like, oh, there's not a problem. This is like, oh, wait, it's really tight when there's a lot of data, and it's really spread out when there's very little data. If anything, we might be underestimating the and we might model this model falls apart. So if anyone has loud noises in the background, hit mute on your mic. So this model falls apart as we go way far out. Do you guys see that? This model just is trash. We go far out, the model is just horrible. So that's a good example of all violations. Right here, we got some more residual.
Okay, and you wouldn't call that heteroscedastic because we don't have a lot of data.
Oh no, this is total heteroscedasticity. Complete and utter. I don't know, can you rephrase that? Because no, did we lose?
Okay, so the last one was definitely.
Yeah, this is the same plot but zoomed in, and that is definite heteroscedasticity. Definitely. Yeah. The previous one, I don't feel like we had enough evidence with. I was fence sitting on it. And it's all right to say that in statistics. It's all right to be
so
like,
for that one, you wouldn't make the argument that you need more data?
This is not the test, right? Good. Because I'm doing it in Adobe. This one right over here with this plot, I'm not going to call it heteroscedasticity. I'm not going to freak out on that. I'm definitely, you see when I actually looked up here and I thought the little hand thing is a point? And does everyone see how if that little hand thing is a point, then it would look nearly perfect? You guys see that? If my little hand thing was a point, this would be like a really nice residual plot.
Can you do serial correlation?
I guess we don't really serial correlation. I'm trying to think of a good way to, like, you don't see it that much unless you're in time ordered data. I don't think we have any really good examples, and I'll drop the hint. I really didn't kill anyone on serial. There is the ability to use the knowledge of serial correlation on the test. Hint, hint. 4.5 minutes till we restart the meeting. I don't think you don't have to super know serial correlation. Serial correlation is just some time order aspect in the data that's causing it to kind of jitter up and down. It's more in time ordered data. We haven't dealt that much with time ordered data yet, and that's why you'll get serial correlation, because it's a time effect that blips throughout your data. But so you can use that knowledge, but don't worry, it won't be something.
I guess I was asking what the residual plot looks like.
Oh, sure. I think the easiest way to do that, let's get one displayed here. Residual plot, serial correlation. Some really good pictures. We're going to see the up, down blip probably. Some of them are harder. You've got positive and negative serial correlation. I oftentimes think of the negative on-off serial correlation. You can see the time-ordered effect. This data right here actually has serial correlation, it looks like, because you see up, down, up, down, up, up, down, up, down, up. The jitter in there is what you see, and you'll see that in the residual plot. It'll be more apparent. This actually is a residual plot. This is a very interesting, it's a residual versus a lagged residual. It looks like they have a non-linear effect in their model too. So we have positive and negative. Ooh, that's some pretty stuff right there. Let's see. Serial correlation is really any sort of time-ordered effect is what you can think of serial correlation as. this is like a long-term lag effect right here. There might be some lag, higher order lag on that. But the best thing to know and understand, I think, our negative serial correlation is probably the most common thing we will see. I shouldn't say most common. It's one of the most easy to identify. If you see a jitter pattern in your data, anything is bad. And as you notice, they have time here because, as I keep saying, it's a time element, and we haven't dealt that much with time data. Residuals! More questions? You got?
Can you go over transformations a little bit?
Sure. Let's see. Let me mark the time thing on transformation. Okay, guys, I'm going to restart the meeting, okay? I'm just going to pop out, pop in. So you guys ready?
Yes.
Okay. Let me quit the meeting. All right, let me go here. End meeting. Okay, we're going to start right back. Hey! Okay. Question was transformations. I am recording again. Okay, we'll wait like 30 seconds. I think everyone should get back in. It only lets me go 30 minutes. I'm not a pro. I had a pro membership. Okay. What's up, Mason?
Oh, hey, you want to hear that, right? I'm just going to leave all that. I mean, are you going to do that?
So, let's talk about, the question was to talk about transformations. And I'm going to lead the conversation in transformations. Let me mark the time on this. Time on transformations. 36 minutes in. Okay. I'll stop right there.
Okay.
So, what was the first question again that we talked about? Oh, it was interaction plots, right? Interaction plots, and then residuals. Yeah, I got my time data when I post this. Okay, so let's go ahead and talk about the transformations. I'm going to kind of lead this conversation to where I want it to go. What we have transformations for, I'll say this, if you don't have a question, probably mute your mic. Like you can click the little thing in the bottom left corner that goes. So mute your mic if you don't have a question, kind of cuts down on noise sometimes. So with this in mind right here, let's think about when and how we use transformations. A transformation is oftentimes going to allow us to achieve normality. So why in the world would we want this? It actually creates the residuals that allow the model to explain the same across. I mean, that's a big thing. It's like when the model achieves normality, then our residuals are normal, we don't have unexplained variation, and all this stuff. So we have the ridiculously powerful command of all transformations, which is ridiculous. Because when it goes through and actually finds the best, oh my gosh. And what we're doing there is we're actually looking at, and I'm trying to direct this towards how I wrote the test questions. I want you guys to know what to know about transformations. The way in which we use transformations are important. Because we can use transformations to do two things. You can use a transformation to add an element. These are the two things I would say you can do with transformations that are really important. You can use the transformation to add an element into the data that normally you don't have. Like a transformation to transform, it's actually doing what the higher order terms do. This is the crazy thing, that higher order terms and transformations can actually do the same thing. Because you're basically looking at the x squared in a model if you square the x, are you not? Does that make sense to everybody? You guys see that? If you're looking at the x squared in a model, you're basically like using an x squared term and looking at its effect. So with this in mind right here, what we need to understand is that transformations allow us to really pick up on, I would say, nonlinear relationships. And we see this a lot of times with the log-log relationship, which is one of the classic relationships that exist. And that really goes towards really spread out data. The log transformation is by far one of the most important because it sucks in big values. The log transformation sucks in these huge values. Let's see if we can go to the screen share here. Oh no, it's the test. It's not the test. Log transformation.
Can you get everyone to turn their mics off because like it keeps interrupting you?
That's yeah. There we go. This is excellent right here. That's awesome. I mean, you can see this right here. They're showing you before and after on a log transfer, or they just logged the Y actually. That's all they did right here. That's all they had to do. If you look at the values of Y, think about the Y as a histogram. All these values of Y, you can see the right skew to the histogram. The histogram is extremely right skew. So when you log the Y, it sucks down all those values. So transformations, if you were to draw a model in here originally, you're going to see a nonlinear element to it. So there's really, I hate to say it, we live in a world today where we don't have to know what every transformation does to the data. Because Dr. Petrie, and I really mean this, wrote such a ridiculous code that tests, I mean, when I did transformations back in the day, it's like, okay, what does this transformation do? What does the data look like? Is this the right transformation for what the data looks like? Now all you got to do is be like, find transformation, and then boom. So you're changing the structure of the data with the transformation, but you really have to realize you are losing that interpretation. Your interpretation's going kind of a little, I mean, it's at least going a little bit. So you have to think about what you're gaining from it. If you find a great transformation that blows up your ability to explain the data or in a good way, makes it really great. Like this transformation is worth everything. The ability to explain now, you're going to go from a line that goes through a data like this to a line that goes through a data like this. And you have to understand the log transformation. It's still easy. What I would do if I had this model is I would solve for a Y and then I would transform it back. Like I'd be like, oh, with this X, you'll get this log of Y value. And if you think about it, when you bend it back, the line's really bending back into the data if you bend it back. So it's a ridiculously awesome model. And with the codes we have, the ability to do this, and they're showing before and after log transformations again here, U.S. population in millions. And if you look at it by a log, is that how high we went? Yeah, it just follows a nice log pattern there. Sucks in all high values. So really, you don't need to know when to use every transformation. You just have to know that with transformations, we can achieve things like normality of residuals. We can achieve things like we can actually take down some heteroscedasticity of the data. You're going to see that transformations can be really valuable, but it's like you're giving away a little bit of yourself with the transformation. And if it's worth it, it's worth it. So that's why in Petrie's, I'm trying to remember which assignment it is, if you look at it, every time you do a transformation, it compares it to your original R squared. And it's not even going to tell you like this is a good idea, because technically speaking, any increase in R squared is a good idea. Any R squared going up is a good idea. So you could be like, oh, R squared went up, that was a good idea. But I would not argue any increase in R squared is a good idea. You're really, it's an exchange. You gotta feel what you're happy with. So if you feel good about it and it really helps your model, that's great. Questions. You guys just want to eat pizza tomorrow or something? We do like pizza day. No test, pizza. Yeah. Are you guys feeling pretty all right about it? How are you feeling?
I'm feeling good.
I don't know. There's just so many things that there's just so much information that could be on there, and it just seems kind of hard to get a grasp of it all.
I think the practice test is it's maybe even fairer than it should be. It's fair. For what the practice test has on it, it's fair. And I'm not saying that it really is fair in my opinion. I've went a lot towards what I've said in class. Like, coming to class, paying attention is going to be a big help. So, you know, in understanding it. There's like, I just actually put a question. I think I'm on page 9 of 10 on the test right now. I'm literally getting close to finishing the test. But these things take a while. Like, I've been reviewing it and everything, but I put a sentence on the test that I've said in class. I was like, this does this, and then this does this. And actually, if you're paying attention to what I'm saying, people tonight will be like, wait, what sentence did Brian say? And it's like, well, then this does this. If this does this, then this will do this to change this to this. There's literally a sentence that's like that on the test. It's like, this will change this, which will change this, which will do this. So there's, you know, do you guys have any idea what that sentence could be about?
Variance inflation factor.
Oh.
If I guess it, I should get 100 on the test.
So, you know, as you can see, I can't say yes or no to such a question, but let's just say I have a good feeling. Do what?
Is it interaction plots? Like interaction stuff?
There is actually, we did interactions before you came in, so I'll let the video, when I post the video, you can check that out because we did a little bit of interactions before you came in, and we kind of nailed it down a little bit more.
No, I saw it.
Oh, good. Yes, more questions. Ask about anything we got. What's the last? I'm trying to think what the last part of the test is that I'm writing right now. I think I actually am writing the transformation part of it, but yeah, there'll be a little bit of transformation on there. Like I'm
it's not going to be like too mathy, right?
No, there's nothing. There's a little bit of like write the equation. There's no like untransform the equation. I'm not going to do that.
Okay.
Yeah, I don't.
Like as long as you know the rule of logs, you should be okay.
Good, but you know, it's not a math. I mean, it is a math course, but it's not a math course. So it's as much of a math course as it. No, it's more of an art course than it is a math course. Keep going with the questions. Whatever you guys got. It's like silence.
Could you just kind of give a good like overview of multiple regression?
I mean, let's think about multiple regression here. Let's think about the new stuff we've added. And let's kind of okay. Let me timestamp this, and I got to remember when people ask questions, like timestamp it. 47 multiple regression. Multiple regression. Okay. Okay. So I'm gonna try to post this like immediately, as long as I hit record every time. Okay, so multiple regression. Let's talk about the concepts and see what we've added to our bank of knowledge. This is gonna be me trying to, like, what concept do you guys want to mention first? Multiple regression that we should talk about. I can name them.
Really, like the kind of the theoretical stuff behind it, like kind of like, I guess. I don't know. I'm at a loss for words for how to describe it. Just the background, like what's going on to make it happen.
That's a really good question. I mean, Angela brought up the naive model, the naive. I never pronounced it correctly. NAIVE. What we're doing is multiple regression is literally built off of simple linear regression. It's just the next step. Because then you just keep stepping forward every time, stepwise regression. We'll talk about that later on. But you're literally just going to one more variable. That's all you're doing here. Nothing too crazy. Nothing to see here. So with this in mind, you have to think about this. When we first started doing a simple linear regression, we asked ourselves, did the new variable explain a significant portion of variation? Let's say naive model versus regression. Let's see if we can get one of those up. Picture. Any pictures? No pictures. A lot of interest. Ooh, that's kind of what we're talking about here. That's a different type of thing, but it almost looked like it. A little crazy graphics. The original model is just the mean. So mean of data. I really should not Google too many things. You never know what's going to pop up these days. The mean of the data is just what's going through the center of it. And we don't see any scatter plot. Oh, scatter plot. Scatter plot. This one's nice. So with this one right here, the mean of the data just goes through it like this. So that's the mean of the data, right? It's just kind of like, if I were to ask you to guess and like guess for me someone's weight, I don't tell you anything about them. So if I said guess someone's weight, and I have no idea why it's 4 or 5, it might be in kilograms or something, but that wouldn't be kilograms. But with this in mind, you would probably want to guess in here. But our new model, when we talk about the new model would be in here. You can see the linear model in this. You can see the linear model to it. So when we compare this to the like kind of just the starting point of total variation that would exist from the mean, we can see that our new model does a much better job explaining. And we would simply graph in the line right here, and you know what I can do? There's that picture. So let's see here. So let's graph in a mean right here. Mean, I'm a horrible drawer with this thing. So there's my mean, and it's a wavy mean. It changes. That wouldn't be right. Then we graph in our model. It'd be much easier to draw. And with our model right here, you can see how much we missed. You can see the residuals from the model. The residuals from the model are just here, little tiny one there. These are all the residuals from the model. So the model has variation it doesn't explain, right? Does everyone see that? The model has variation it doesn't explain. But the mean does a much worse job. The mean has so much more variation it doesn't explain. I mean, these sums of squares, if you were to make squares out of these and look at the sums of squares of them, all these squares are huge. I mean, they're big. We're not explaining well with that line. It's horrible. This is the important part. This is simple linear regression. When we start out by looking at the mean and say, what's the total variation? And then we step to a model that has one variable in it. So at this point, we've explained, I don't know, 60% of the variation. So with this 60% of the variation explained, we now bring in another variable. And then we see how much we're missing by there. Because we could redo like our misses or our residuals, right? If you make a new model with more variables in it, you'd probably the residuals will be smaller because it will do a better job. The residuals that's what it does. We add it in to explain. So with this in mind, right?
As long as there's no multiclinearity, right?
Even if there's multiclinearity, the worst possible that can happen is that it doesn't go up. I mean, your R squared does not go up, and the sums of squares explained don't go up. Does that make sense? The worst possible thing that could happen is your new variable explains nothing new. It can't unexplain stuff. Like if something's explained, does that make sense? If something's explained, a new variable can't unexplain it. Does that make sense?
And then if something's not significant, you just drop it out of the model, right?
Oh yeah, totally. I mean, you bring in a new variable and it's crappy, you just say like, nope. You're just like, nope, not staying in my model. And so, but you have to realize, I mean, I'm gonna pull up something here. I have a lot of fun data sets. I'm always messing around with data. This is craziness. So, oh, what's the tip of the day? Like, oh, select multiple bars, and oh, that's awesome. So awesome. I didn't even read it. So I love these little data sets here. I've got tons of different data sets. I even do my grades in JMP. Like I love JMP so much that you can see here like grades like on project 3 data, like final grades. I do my students' grades in JMPs. I got something more interesting. Mario Kart data, project quick. Oh, this was fun. So you guys took Stat 201, right? You guys took Stat 201, right? You did projects? I actually wrote in the scripts into JMP to create like the output because I got tired of, I didn't really get tired, but I was like bored one day and I was like, I wonder if I could just make it so I could actually like hit run script and then it would like basically do certain parts of the project. So if you hit run script on these, it actually does parts of the project for you. So I shouldn't say it, but a really smart student could be like, oh, that'd be horrible. It'd be dishonest and be a violation. So let's look at something we haven't seen yet, but something kind of cool. I love this, and I'm waiting to see, like, I really want to talk about the Petrie and see, like, everything he has. It's a small data set. Okay. enough little aside. Let's see let's see what we want to see here. Let's get to the real point. Okay, here we go, window list. So let's go ahead and analyze. Let's go to fit model. Let's remove out. When you get used to jump, it's just one of those things. I want to predict someone's, let's predict someone's high school GPA. So I'm literally taking all my quantitative variables right here, and I'm going to predict someone's high school GPA. So what I'm going to actually do is a later concept, go to stepwise regression right here. I love me some stepwise regression. So this is not something you have to know right now, don't worry. But with this stepwise regression, I can actually see the p-values in my model and what's going on right here. All the p-values are over here. Just ignore them for the moment. Actually, I mean, you can just click on this one right here. Look at this. Study time and party time are significant in predicting someone's high school GPA. Does that make sense to you guys? And do you see these over here?
And like Candy Crush isn't.
Do what?
Like Candy Crush is not, obviously.
I can actually tell you, this is actually all the single variable models, and I'm so used to Jump. I'm a lot quicker in Jump, as you can see. This is interesting. We'll talk about this just briefly. Why is age significant in someone's high school GPA? Why is age significant?
Because not
They
everyone's
fail
in
and
high
have
school.
to take it again.
The older you get, you're going to take harder courses most likely, and so the older you get, there's a greater chance of having a worse GPA.
Well, it's high. Ooh. Possibly. I do agree. I hadn't thought of that. You're saying like people who fail and like have to retake, and by the time they're in college, they're older.
Well, like so like as a freshman, I'm going to take like.
Remember this high school GPA.
Okay. Yeah. So. I guess I'm taking like geometry or pre-algebra,
okay.
And then say come senior year, I'm taking AP Calc. So there's probably a greater chance that I'm going to fail Calc because it's a harder course.
Oh.
But if you do well in the earlier classes, then
this data was collected on people at UT, so it's all retrospective. It's all they've already completed all their high school. So I totally agree that as someone gets older, their high school GPA might go down. I think that's perfect. And I was also thinking about the whole fail thing. The reason this exists in this data, or at least I believe, is in like the 70s and 80s, like for our older students, if you did high school in the 70s and 80s, they didn't have like a 4.5 and a 5.0. There's a lot of grade inflation. So older students weren't subject to the grade inflation that students, you see what I'm saying? Like in these 80s and 90s, if you had a 4.0, everyone's like, holy crap. And how many people do you know who graduate high school now with like a 4.0? It's like, oh, I had a 4.2. And you're like, what? Well, yeah, I had a 4.4. A lot of grade inflation. I believe that's why. Scholarship tells us GPA. You can look at what's significant. We could even make a cutoff here for our simple linear models. All those variables are significant in a simple linear model. I mean, and as you can see, I know Jump is what I know, but I want to get better at R because I just did all the simple linear models in there we go. And we've even got the right there. So let's go ahead and look at some crazy stuff now. So I'm going to go from a simple linear model. Let's just make a simple linear model. Boom, simple linear model. Now I'm going to go to a multiple regression model. Boom, multiple regression model. And I love this because I can actually look at my R squared adjusted up here in my R squared. It's just easy switch right here. And if you notice, height is actually significant in the model. It's probably a gender effect is what's going on there, a lurking variable of gender. So we have height right there. Let's take something else. If we go down here to scholarship amount, scholarship amount, does that tell you someone's GPA? Yeah, it does. You can see what happens there as I switch it. You can look at the R squared and R squared adjusted. The root mean square error goes down. We want that. Best of all, with stepwise regression, we can just hit go. You're not liking me today? There it goes. I can just hit go, and it's going to create the best model for me. For multiple regression model. And this is, there's this type of stuff in R too, but it's got all these in the model and it tells me what it did, taking things in and out. But when you do this right here, like if you watch the estimate, like let's look at one with a higher estimate, like age. The estimate on age, if you notice, actually changes. Do you see that estimate on age changing right there as I add in another variable? Even
yes.
And the significance on age actually goes down. So this is with the variable out, and then I add in the variable, and the significance on it went down. It became less significant because it went to an E negative 18. I kind of like jump for the like quickie things I can do here. If I remove party time, you can look at the top one there, or just look at the one below it. You can see it changing. You see the p-values changing. Everything's being recalculated because when a variable comes in the model, it starts eating away at the variation other things have. It steps on their toes, and everyone's all fighting because, party time added into the model right here only explains about 1% more variation. But if I go right here and just add party time, well, that explains about 1% variation still. Let's go. And continue cycling, cancel. So I have a different model here because I started at a different starting point. More on that later. But age, when I remove it out of the model, explains about 8 or 9% more variation. But when I put age in by itself, it explains 10 because it's stepping on the toes of the other variables. It can only explain what is there to explain. And all these variables, I've got tons of variables. They all might explain on average like 4 or 5%. But if I put everything in, if I go to enter all, it's not going to like me. I can only explain 21%. And if you look at my R-squared adjusted, that R-squared adjusted is hurting. The R-squared adjusted is penalizing me. And if we take out stuff, let's go here. I wish I could sort these. Let's take out a really high one right here. And you'll probably see R-squared adjusted go up. Everyone see that right there? Here's with it in the model. I take it out, and R-squared adjusted went back up. I mean, that variable I had in the model, which has a p-value, TV time per week. But, I mean, do you think TV time tells your GPA to a certain degree? Here's the crazy thing. Remove all. TV time, it's more significant, but it's not significant. It's nowhere near significant, but its p-value is not in the 0.8 anymore. It's down to a 0.3. That's a big change in p-value, but not significant. Does everyone see what's going on here with multiple regression, with tons of variables fighting each other to get in the model?
I feel like multicollinearity is going to be like 20 points on our test.
No, it's probably about 10%. You guys got some good hints tonight. I'll say that. Wink, wink. I didn't go crazy on multicollinearity. You just have to know the concept of it. You have to know what it means. I think we did a really good job talking about it a lot. Like multicollinearity. You see, here's the thing I like. You see, I know how to do a lot of this stuff in Jump like this. Because if I go to enter all in Jump, run model, let's go ahead and run the model, and then I go down here to my estimates, and I click here, I go to columns, and I go to VIFs. There's all my VIFs in Jump. And funny enough, they don't step on each other's toes. I've done this stuff in Jump like a billion times, so you guys don't get to see me in class like clicking around like I'm a genius. You guys see me like fumbling like a fool. So these are all my VIFs right here. The intercept does not have a VIF, so we can put them in descending order. The model only explains 20% variation, so technically under Petrie's rules, that would be 1 divided by 0.8. So you could even say that some of these have issues of multicollinearity. You could. I'm not super concerned. It's just kind of a crappy model. Like, it's crappy for other reasons. Like, I'd first start attacking...
You only know that multicollinearity is present when your VIF is outside your threshold, right? When it goes above your threshold.
And there's a question related to that tomorrow. You guys gotten a few hints tonight, which I'm fine with. You come to the review, you watch the review, you get a few hints here and there. The formula for the threshold is 1 over 1 minus r squared, which is the formula we use to calculate the VIF. The VIF for an individual. 1 over 1 minus r squared of the ith term, which is the ith x variable being predicted by all other x variables. Let's see if we can display that VIF formula. And they probably will show it here. VIF, R is my friend. It's going to show 1 over 1 minus r squared. Really? Not going to show me that? Okay, here we go. We should see 1 over 1 minus r squared. Really? Hey, there's our formula of the ith term. There's our formula. So it's VIF for the ith variable because you have tons of variables in your model. My lights are on. It's really dark in here. So VIF of the ith term gives us the following. And this is also the formula for the threshold, and that's why my mind kind of exploded. I don't know if Jump actually will denote. Jump really holds your hand at time, which is not bad. Jump held my hand to me learning statistics. That's one of our other models. That's our here's our fitted model. I don't know if I hover over it. Oh, variance inflation factor, a measure of how inflated the standard error is due to collinearity among regressor columns. Regressor columns are your X's. Standard error is your estimate of the truth. So it's saying your standard error is inflated. That is literally the textbook definition. And these are some of the reasons I do like JMP. You hover over something in JMP and it tells you what it is. You're just like, oh, I want to know what the estimate is. The parameter estimate. This estimate, the estimated coefficient in the linear model. Well, I guess it's a multi-regression linear model. So yeah, I guess so, JMP. Yes, you're right. Standard error, the estimate of the standard deviation of the estimate. So a standard error is a standard deviation. T ratio, it's going to say the 2 divided or something. I've never hovered over each one. T statistic, an estimated standardized is a standardized test statistic. This is close to normal distribution. Oh, it even says it's close to the normal distribution. I love you, JMP. I say that all the time. No wonder. I learned from JMP. But as it says. So lots of good stuff in here and lots of output. And this is the output I see every day. So I'm used to JMP output, and I've been working with R more. No! More questions. Let's talk about what other concepts do we not cover? We talked about...
Yeah, I have a quick question, if that's okay.
Sure.
So if you have Spearman's coefficient, if you square that, is that equal to R squared?
Yes, because you're just looking at, it's just how well it does in explaining it. And I'm 99% certain of that. Like, I feel like this little twinge of like, wait a minute. But Spearman is the ability of the nonlinear relationship being explained. Excuse me, not nonlinear. Nonlinear. It's got to be monotonic.
Monotonic, but not non-monotonic.
Yeah, if it's non-monotonic, Spearman's not going to catch it very well. So, and that's good test question stuff too, because that's definitely on there. So the R squared would be the percent of variation explained by a Spearman correlation. So it's just how well it explains and it's the variation in ranks. Like, it's variation explained in ranks. Does that make sense?
Yes.
Yeah. So you're explaining all the variation in ranks, which is what you're doing. I mean, it's good. It explains 100% of the variation in ranks. Does that mean you understand 100% of the variation in your data, though? If you understand 100% of the variation in ranks, do you understand 100% of the variation in your data? Oh, perfect test question.
No.
No, you just understand if the next one will be bigger or where the next one will be bigger. You understand 100% of the variation in how the ranks go, but not 100% of the variation in, like, you know. That's a really good question. But it's definitely an R squared. It's percent of variation explained in ranks. More questions. Nice question. Who asked? Did you ask that or Chris? Someone else. Chris. Nice question, Chris. It's really good. I think someone else asked me that too. Maybe you asked me that. More. We can go for a little bit longer. Just if you guys got questions, we've been going for. We can at least go to this.
I'm looking.
Is there anything in multiple regression where you haven't hit?
Yeah, we'll go back to Josh. Did you? And then we'll check out Angela's. I'll see if I can think of more in multiple regression. That.
Okay. I'm on question 7 of the practice test.
Mm-hmm.
And
let me not open the actual test. I mean, that'd be end of the world stuff, you know.
You forgot to send everyone the other test.
Oh, I did. I'll send that. Okay, Angela. If I don't send that out right after this, I went to class. I came back. I responded to emails. I think a few of you guys saw I responded to your emails, and then I worked on your guys' test, and then I ate food, and the bowl's still next to me. So it was some good food. So yeah, it's been busy. Okay. Oh wait, I was about to click on the test. Okay, here we go. Question 7 on the practice test. Okay, let's do that. Where is it? Where are you practice test? My brain is breaking, Josh. There it is, exam 1. Here we are. Okay, let's scroll down. Okay, good. Petrie's test. I put my own meme on there. Let's scroll down. Quick scroll down.
Make sure you sleep tonight because you won't get to tomorrow.
Oh no, yeah, it's gonna be tomorrow's big. Okay, question 7. Oh, this is all the. Wait, where the hell is question? Oh, here it is. All right, question 7. I think it's about where we stopped in class. So question 7, in multiple regression, we look at R squared adjusted instead of R squared. Why does R squared adjusted get a fairer assessment of the fit? And really, it's the penalizing factor here. R squared always gets larger when junk predictors are added to the model, while R squared adjusted doesn't. And I think that's the answer. I haven't read all the other ones yet, but that's the first thing that, when I saw junk, that was, R squared is always going to get larger. And I don't, because technically, as we've said, it could stay the same, theoretically, but usually it's going to get bigger. R squared adjusted uses a more accurate estimate of the typical error of the model. No, it's just penalizing you. R squared adjusts R squared based on the sample size of the data. Yes and no. That's not the key element of it. It's not, yes, it does take into account sample size within the penalizing factor, but that's not the key element of what it's doing. It's not saying, oh, your sample size is this. I mean, R squared already looks at sample size, so it's kind of like, yeah, they both do that. So R squared does that. R squared adjusted takes into account the correlation among the predictors. No, that's multicollinearity. So that's confusing you between multicollinearity and R squared adjusted. R squared adjusted is unstable when many predictors are added to the model. That's very not true. R squared adjusted could be really good with tons of variables in the model. Like, I mean, you could have a really good model with a lot of variables. So it's not unstable. It generally will decrease. Generally speaking, R squared adjusted, oh wait, so it says R squared is unstable. Well, and here's the literal thing, is that you could have an R squared adjusted and R squared that are really close. So R squared, there's no difference between R squared and R squared adjusted other than R squared adjusted has a penalizing term. That's literally all it is. I mean, I think looking at the formula is a decent idea in class. We're never going to solve it. But R squared adjusted just has a penalizing term.
So are we ever going to hold like one kind of above the other? Like,
no, one's not better than the other. R squared is always the one you're going to interpret, and R squared adjusted is always the one you're going to use as a diagnostic. R squared adjusted is a diagnostic to see how the model's doing. Like, it's like, okay. R squared adjusted is a should I use this model type of measurement. Like if you have a model and you take a variable out and R squared adjusted goes down, then you know their model's doing well. Yes.
I mean, R squared adjusted goes down.
The best way, the easiest thing to think about is if you take out a variable and R squared adjusted goes up, then it's like, oh man, I needed to take that out because that variable was hurting me more than it was helping me. So yeah, if you build a model and then you take out a variable that has like a p-value of like 0.03 or 0.04 and your R squared adjusted goes up, then it's like, oh well, that variable was really, it could have just been significant by chance. So yeah, it's a diagnostic. You never really interpret it. You just say like, how's my R squared adjusted doing? Because then it's adjusted.
You want to go up.
Yes. If at any time it starts going down, and that's when you start, like, if you graph, I bet you, like, I know these pictures exist because I've seen them. I make them. R squared versus R squared adjusted. It's showing it right there. We should see an image of it. Is this person graphing it? Seriously, someone's got to show their two in tandem and, like, the two diverging. No one wants to make my pictures that I make. And I tell you, in grad school, you have to do like 1.5 billion visualizations. Like, visualize this, visualize that. There's our formula for R squared adjusted. What we're generally looking for here, if I were to see it, you would see a line constantly going up. No, that's not it. You'd see one line constantly going up because R squared is going to go up, but then you would see an R squared adjusted that can go down. Well, shoot. I can make one. Let me just make one really quick. Let's look at an R squared versus, is it going to, I got 2 minutes. I think I can make one.
Can I ask you a random question really quick?
Go ahead. I'm going to try and make this real quick.
It's like really short.
Sure.
You said violin plots were going to be on the test? Well, that we need to know
they're
about
not on the test yet, actually. We talked about them for moments. Maybe I said they'd be on the test and then I forgot.
No. Okay.
Maybe that'll be.
I won't look at them then.
Yeah, don't. If I mention something in class shortly and it doesn't seem like a big concept, I don't know. Don't worry too much. Don't Did I get R squared adjusted on these? Well, let me save R squared adjusted columns. You're not going to give me R squared adjusted. Dang you, jump. Well, I wish each model would let me save the R squared adjusted on it, and we could see a ridiculous amount of R squareds and everything. I've saved them for each model and then graphed them. I mean, that's if you really want to do model comparison, you take all your models and you compare all the R squareds adjusted. You see what I'm saying, right? You build 3 models, and then you make a table of your values that come from them. That's model comparison is a big thing. And I've actually done an all possible regression with all types of, I've taken models of up to 8. And actually, wait, oh, that's the root mean square error, which we want root mean square error to go down. So, man, jump is powerful. There's my best 8 variable model down there, you can see. So it's highlighting each best 2 variable, 1 variable, the best predictor of so much stuff. So don't worry about that. That's more to come later on all possible regression. But so the biggest thing here, as we were saying, it's about to get cut off, is R squared adjusted. What's up, Josh? It's gotten progressively darker in my apartment. Like, you can barely see me now. Like, I don't even know. I'll turn on the light here. There we go. Probably should have done that a while ago. All right. So R squared adjusted is a diagnostic. I think that's one of the big takeaways. R squared adjusted is a diagnostic. We are recording, right? Yeah, we are recording. Good. R squared adjusted is a diagnostic that lets us understand the effect of adding more variables into our model and whether or not it was a good idea. Synonymous or not synonymous, but a related understanding is the partial F test, which is going to, I'm writing a note to myself. I wanted to make a note of something. So the partial F test and the R squared adjusted are related. They look at the impact of adding more variables to the model. They're diagnostics. So it's the idea of, are we doing the right thing here? It's a diagnostic. More questions if you got them. Talked about interaction plots, residuals, transformations.
Will you go over chi-squared real quick?
Sure. I mean, so, and this goes back to the start of everything. The chi-squared, and we don't really reference it as the chi-squared, but you do need to understand how we're calculating. Let's look at a contingency table. So let me pull up contingency table here.
Like marginal and conditional?
To a certain extent. I didn't make it too mathy. I didn't want to kill you guys and be like, let's do math. Let's go here and let's share the screen again. Thank you guys for coming tonight. Appreciate it. Hey, we got cat versus dog person. There's some fun data right here. Cat people, dog people, or cat dog people. I mean, you can look at this data right here and you can visualize it. Is there much of a relationship or association? What would we use? Is there much of an association between someone's gender and their preference in animal? Oh, my head was going at it.
Yes.
Oh yeah, those are ridiculous. I mean,
yeah.
If you say like 10 guys like cats and 42 guys like dogs, meanwhile 39 women like cats and nine women like dogs, it's like, whoa. And we can see that. If we were to represent this by a mosaic plot, is on some study page or something, I would think that who's ever putting this out here is going to show me the mosaic plot too, because a mosaic plot, they're not going to give me a mosaic plot of that? Damn you. What we have going on right here is a lot of feedback noise around going for a moment. What we have going on right here is that we're trying to analyze the association between X and Y. It doesn't matter if you flip them Y and X. So with this, we need some sort of value to analyze the difference. Key part of what I'm saying right here. This value we will call a discrepancy. Now the discrepancy is also...
Discrepancy?
Mm-hmm. The discrepancy in other classes, and even in Stat Tool 1, has been called the chi-squared statistic. Now, what we have, the way to achieve the chi-squared, which is the discrepancy, same thing, we're just using different words here. The discrepancy will be obtained by doing observed minus expected squared over expected. So we're actually looking at this cell and saying, well, what did we expect to happen? How much did this deviate? Let's square that, and then let's standardize it. We're taking a difference between observed and expected, squaring that difference, then standardizing it by dividing it by expected. So all you have to understand is that's the idea of a cell chi-squared or a cell discrepancy. We could call it a cell discrepancy or a cell chi-squared.
Yeah, okay, I just didn't know it was synonymous with discrepancy.
Yeah,
that makes a lot more sense now.
And so, so we're 99% the way there. We automatically take all these discrepancies and add them up, and that's the discrepancy for basically the whole test. If we add each one, which then that's cell chi-squareds added up equals total chi-squared or Pearson chi-squared. So if you add up all the discrepancies, you get, and did we mark this one? Let me kind of figure out half what time we asked this question, because this is, I didn't mark it. No. 47 minutes, so we'll mark this as 1:18. I'll mark that in the time thing. It was a little bit before that, wasn't it? 1:15. Chi-square, or discrepancies. Yeah, chi-square. Associations. Okay, yeah, so, you need to be able to kind of look at this, review the notes a little bit on it. I mean, the earlier chapter stuff I didn't go killer on. I didn't, pick out a little tiny detail. Anything on the test on this stuff I said in class. It's in the book, it's in the notes, and I said it in class. So if you took notes on what I said in class and you read those over, truthfully, I think if you took notes, even though I'm a little crazy in class, I know that. But if you took notes on what I said in class, I think you'll do pretty well. But then you have to reinforce it, because it's the things I say, it all makes sense to me. And I realize, because I've been doing it for so long. So I can't see how, when you increase when multiclinearity is a problem, I know what happens. You ask me, why is multiclinearity a bad thing? I could tell you right now, just be like, here's what's going to happen with multiclinearity. And then if you ask me, would you still use the model? I'd say, well, yeah, depends on what use I'm going to use it for. So these are the discussions we need to have sometimes.
So we definitely don't need a calculator, I guess, at all.
It wouldn't hurt. I would say maybe 10 points, maybe up to 10 points on the test could be. It's not like super calculator stuff, oh, you better have your TI ready. You could probably do it in your head. It wouldn't hurt.
I can bring my financial calculator?
Yeah, you can bring whatever you want. You can bring, as long as you don't use a phone.
Okay.
As long as you don't use your phone, you're fine. But yeah, none of it's going to be, there's no math heavy stuff. It's not the point of the class. What are you guys thinking?
A little better.
Good. I think some of you guys working really hard.
I know this was asked before, at least a little bit, but can we kind of go over interpreting the residual plots and the diagnostic plots again?
Sure. Residuals and diagnostic plots. Let's hear. Write it down. 3:30.
I'm going to go finish my note sheet. Thank you for helping, though.
You're welcome. Good luck, Angela.
I don't know. I just seem to have a block when it comes to.
I mean, I like doing if we bring up histograms right here, histograms are going to show us, you really need to see something that's a unimodal shaped histogram, anything that looks crazy like this. When you get a histogram of residuals, you're really looking for something like this. This is for the normality of the residuals. Like any histogram of residuals should look. This one has a right skew. But if we go to, is there a specific test you want to talk about, or do you want to, we could pull up, let's pull up, let's go to, which activity? Let's go to activity SLR. Let's go down here and look at some and just kind of talk about it. We need to go to solutions so it has it. Okay. So here we go. Excellent. I can tell you right here, you guys have seen this one, I think, but, I can tell you this fails the non-normality in here. That's the issue of non-normality.
Because of that little
dip
right there.
That's an issue. And here's the thing. Anywhere you see gaps where it goes too much, you see how it's too much there or too little in here, if you see too much or too little, that's a problem. And nothing's going to look perfect. It looks pretty good in here, but then you get bad and you get bad out there. And then the bend in here, that's bad, that's bad. But I don't really see heteroskedasticity. So equal spread and nonlinear. My smallest p-values are going to be the normality. So if we scroll up here, normality has a really small p-value, and the equal spread is the least worrisome. Do you see this little kind of flow through here that could be a bend? That's what the linearity test is almost picking up on. The linearity test is seeing this little bend throughout here that we're seeing like this. Do you see that, Josh?
Mm-hmm.
That's why that test almost comes out significant. The equal spread is looking at this right here. So this is me checking the equal spread, and that relates to this. So this is me checking the equal spread. And then if we go to the normality test right here, I'd look at this, and I'd say, okay, there's white areas in here. There's too much here. There's too much here. That looks bad. Oh, no, we got this here and this here. And there's a lot of points. So since there's a lot of points, it's looking pretty bad, and that's a low p-value. Do we have another test? Oh, we got some prediction versus, look at that, nice. Oh, I love that. Definitely know that. Prediction interval versus confidence interval. Prediction interval, of course, is the wider one. Unless you have an R-squared of 100%. Not going to do that to you guys on the test. Going right here, oh my gosh. Oh my gosh.
That's bad.
Oh, this is like, I mean, and here's the thing, because you can almost tell where this question is going. If you think about it, this question is leading us down the road towards a what? Like the point of this, what we're eventually going to do with this is what? I'd say
make a transformation.
Or fit a different type of model. I mean, this model is doing, there's this nonlinear aspect to it right here. There's the nonlinear. If I were to draw the nonlinear, I would draw around it like this, and I'd put an arrow and it'd be like, not linear. And then if you see there's the too little here and the too much, and there's the swing out there. Equal spread, in truth, equal spread is going to be our highest p-value. I don't know if we get the p-values. Oh, called it. You see that? That's statistics right there. There.
Would you
what?
Would you also say for the scatter plot of the residuals that you need more, like you don't have enough data in the front end?
You're saying to truly understand it?
Yeah.
I mean, I can see that argument, and that's probably why the equal spread is one, the model says we don't have a problem with equal spread. So I mean, it's in the. I'm not saying you would reject for that because statistically speaking you can't, but it's getting to where I'm concerned.
Yeah.
Some statisticians are like, no, you can't be concerned about that at all because it's 0.06, and that's not how we do it. But whatever, I don't do my things that way. I'm a different kind of statistician. Take it. So this is what happens when it gets late at night. But with this in mind right here, when you look at this, the equal spread, if you just kind of do this and think about the equal spread of it, it's not that big of a difference. It's not really, you look at it like it's not changing in spread that much throughout the model. I mean, you can look at it up here and look at how spread out those points are, and it's not really doing that. I do see how we don't have a lot of data, so our lack of knowledge wouldn't go towards either way. It's not like, oh, we don't have much data, maybe there is a problem. It's, oh, we don't have much data, well, then we don't have evidence of a problem. Does that make sense? You can't be like, oh, we don't have data, so maybe there is a problem. It's, oh, we don't have data, so we don't have enough evidence of a problem.
It's just they're so much harder to interpret when they're really small. And
which ones? These down here?
Yeah, and like you showed Chris earlier in the meeting, I think there was something from a chapter 7 homework where we did the polynomial model and you can't run check regressions, so we have to those are so much harder to interpret for me.
Yeah, these like I keep saying, if I were to add 1 point up here, all of a sudden this would look super nice. And sometimes you have to think about it in a 1 point kind of understanding, like, oh, if I add 1 point, well then all of a sudden none of these things really are outliers because, like you look at where that hand's at, it kind of makes, everything's pretty equal spread. Remove it and you say, it's just nothing is glaring. And that's the thing is, you don't want to really, if you stare at these two things too long, you'll see something. It's like one of those magic eye images. You will eventually see something. You'll be like, oh, that's weird. Look, it makes a smiley face. Look, it's a sideways smiley face, like a clown. I don't know. You just come up with weird things. Like you can't randomly make a sideways smiley face. But you really, these are the kinds of ones that just like, there's no, if someone told me these were good residual plots, I'd be like, are you crazy? I'd be like, nonlinear element, non-normal residuals. I'd be like, equal spread, I don't know, I'll look at the test. And that's exactly what I did. I couldn't really get a good gauge of the equal spread from this. because there are ones that are obvious equal spread problems. And this one, I'd look at the test and I'd default to the test. I'd say, I don't usually look at models with this kind of weirdness to them. But this is a throwaway. This model is not doing well. This model, I would not have faith in it. I mean, because literally we're way off predicting here. Predictions are crap. And then all of a sudden, if you look at what the model trend is going to be, it's going to do that. And we're going to go down here and transform. After we do the transformation, you can see what happens. Are things perfect? After the transformation, is everything perfect? It's funny, our p-values actually get worse. But when you look at what you have, the model is actually doing way better. The model goes way up. I never like anything saying 0 for a p-value. That's probably one of my biggest pet peeves is if something says 0 for a p-value, because it shouldn't be 0. Just tell me how many decimals it has. I'm cool with that. So yeah, because here we see the original model was 52% R squared. The new model is 84. When you go from 52 to 84% R squared, that's awesome. You look at the problems. The problems are out in here. Is the model, you can see now we have an equal spread problem. And if you were to zoom in on this area, you would see how it spreads out here. There's, even with a lack of data, to get points that far out, there's an outlier residual problem. There's an equal spread problem. There's no longer I don't really detect a nonlinear relationship to this model, even though the nonlinear test is coming back. I can't see it. You see what I'm saying? Like I can't, maybe because it goes like this, maybe. It's not as evident.
Yeah.
Yeah, in the
like
previous
downward.
Yeah, in the previous, that's obvious nonlinear. Like that's where it is. That's why it's rejecting. And then in this one, it's got to be because of that. That's why it's screaming at me. So that's why that one's screaming nonlinear. Heteroscedasticity is getting mad because of this right here, and that. That's why heteroscedasticity is freaking out. Normality is freaking out. Go ahead.
What's the feature that would like scream nonlinearity? Like
nonlinearity?
Like in the one, yeah. Like if you scroll up to the one earlier.
If you put a line through this and it bends, if you want to check put a line through it and it bends, and that's why when we come down here, if we put a line through this and it bends, you want to be through the center of the points at all time. Like you want to be through the average, because if you look, when I put this bendy line in here, I'm going through the average of the points. You see that? So I'm going through the average.
Straight curve.
Yeah, and so that's total nonlinear. And then if I go through the average of the points down here, it might be something like this. I don't know. It's hard to see. Maybe I need to zoom in or something. But that's why I like my jump, because I don't got to write a code to zoom in. I just click the little zoom in button. Oh, I'll zoom in on that. So I'm quicker in jump. But like you guys keep saying, I need to talk to Petrie. I didn't do that yet. But you know how to use R, and you're a superstar. You're not Brian Stevens. You're superstar Brian Stevens. So it's way more versatile. So yeah, I can see the hardest one to see here is the fail of the nonlinearity, residual, gap in model. So this actually gives us a gap in the model now. So there's a gap in the model problem. There's an outlier problem. There's non-normality of residual problem. There's heteroscedasticity problem. But model explains a lot of variation. I'd ask my employer what we're using it for and if they can accept these problems, and if this is the best model I can come up with. It's like it's a give and a take. It actually does worse. I wish the p-values showed me the digits, but it does worse with a lot of the p-values. But in exchange, I get this much better R squared. It's looking decent. Like, yeah, I don't like all these problems. I would tell my employer. I would say I would not make predictions. I would not use this model past certain values of X right here. We could scroll up and see it on here. We could just make a cutoff. I probably would even delete everything out of the model from there. And I'd say I wouldn't use it past this point. Like your error is not consistent. So I would say if the model really becomes erratic after this point, it's good. And I'd just say we don't know what's going to happen really well after that point. So
can we save that kind of stuff on the test? Kind of try to save the day for the model?
Yeah. I think I made the test the test is really clear. I think it's very because when I grade it, because believe me, I'll say this on video. I wanted things to be graded a lot quicker for you guys. I obviously do. I really do. And so this is my present to you with the test, with your guys' first take home, is that it's going to get graded. Like, I'm literally going to come here and lock myself in my place. And hopefully you don't get an email on Friday saying like, hey guys, I exhausted myself. Have the day off. You might get that. Like, drop your projects your things in my box, because I'm not gonna sleep until your tests are graded. You will be getting them back on Friday. And then on Monday, I'll do it. I'm gonna do it. I'm just gonna power through. You get it done, and then you're done with work. That's the way I roll when it comes to stuff. If I got stuff to do, I do it. It's done. Boom. So yeah, because I mean, if I don't, I got my test. I have my test Monday, but it's like if I don't, then I'll have more work next week. You guys are gonna have more assignments. We'll have more teaching. It doesn't stop. Me saying, oh, I'll do it Tuesday night or Monday night doesn't stop it. You just got to pick your things. You literally sit and eat dinner while you're doing work. That's what you do. So you just pick your battles. More questions if you got them. Man,
I had something in my head. Now I'm blanking on it.
Sure. Whatever you're thinking.
God, that was a good question too.
Oh no!
Oh yeah. Polynomial models. How heavy are you going to test on those?
I want you guys to. Here's the thing to grasp, and we'll timestamp it. We'll timestamp this question. Polynomial models. Where's my little clock thing? Hey, F. Ah, no! You didn't see the meme for the test. Here's the meme for the test. You guys watch How I Met Your Mother?
I've seen a few episodes.
Challenge accepted. It's what Barney Stinson always says. Did I close out my clock? I don't know. Okay. Well, I don't know. So, yeah. So that's the meme for the test. Whatchamacallit? Polynomial stuff. Okay, so this is important stuff I want you to understand about that. Is that polynomial terms allow the model to bend. It's a lot of what we talked about. So you have to, the beauty of the program he's written in R allows us to find the correct polynomial term and to see, it's going to show us the R-squared adjusted, and it also shows us the AIC. So that's another topic for another day about model information lossage. But it shows us the R-squared adjusted, and it allows us to understand which one we should enter in by maximizing R-squared adjusted. Because if R-squared adjusted starts going down, it's like, oh, well, this was a bad idea. So it's already penalizing. So we understand that we would expect it to be significant. There is the idea of model hierarchy too, that if you add in a fifth degree term, you must have in the fourth, the third, the second, and the first. If you add in an interaction, you must have in both the variables that are in the interaction. So that's the idea of preserving model hierarchy, very important stuff. So what I really want people to know with transformations is that the idea, or higher order polynomial terms, I want people to know that they're used to add nonlinear elements to the model. So when we have a model that has a bend, we can add in a nonlinear term. And that's assignment 6. When you look at those first few plots, it's assignment 6 I'm thinking about. Assignment, homework 6. We get into some fun homeworks coming up. I like them a lot. I really mean that. When you look at these plots right here, you're inspecting almost for nonlinear elements. And this right here might have a slight nonlinear element to it. So maybe, does that look a little like a parabola to you?
Slightly.
So I bet, let's see here, this is the data set. I'm thinking, I always forget these commands off the top of my head. Okay, good. Let's just ignore the data down here. Let's ignore that down there. I don't think that's going to help anyone with the test. Okay, so this data set we're working on, this is homework 5 data, is it? I want to do something here. This is homework 5 I had open, right? Correct?
Yeah.
And it's the temperature data set, right? No, it's homework 6. This is multiple regrets and stuff. I just need the temp data set. We're going to see if I can, how good of the data sleuth I am. It's bike data. That's what it is. Okay, so let's open the bike data here, and I'm just going to call it temp. That's all like that. Yeah, this is the right data set. There we go. Effective. Everything's got to be all like long words, doesn't it? Okay. So, okay, good. I'm not go over there to that. Okay, so let's think of this right here real quick. I got my data loaded in, and I want to put in a model with, let's create awesome. We'll call model awesome for awesome. And let's create a linear model right here. And let's predict, what are we predicting on this assignment again? We're predicting demand, correct. So let's predict demand. And where did we see the effect? We saw the effect between, that's not the right homework. Here it is. We saw it, demand might, an average humidity, AVG humidity. Okay, that's how you spell it. So AVG humidity. And I think I should get, could not find, of course I'm going to do something crazy. What am I doing? Oh, don't I have something? My brain is not on, guys. This is what happens when you write too much code. Brain dies. It's not capital. Value expression, demand not found. I don't tell the data set. Data equals temp. Average humidity not found. How do you spell it?
Oh, you left out the eyes.
Yeah. I left out the what?
The eyes and humidity.
Oh my gosh. Let me see. Humidity. AVG humid. So am I still misspelling it right here?
The first time, the first one. Right there, yeah.
Oh my gosh. Oh, it's a long day, let me tell you that much.
I bet.
Yeah, it's just brain falling apart on me. Okay, so it's not including my term when I do that. Is it poly? Let's include poly. Let me call the poly command right here. Poly, and then you put in your variable, right? And then you put in the degree. So AVG humidity. That's how you call the poly term, right? Cool. Okay, there we go. Look at that. What'd I say? Do you see it? Do you see it? No? What I postulated was, is there some sort of significant parabolic effect between demand and average humidity? This plot right here, do you see the non-parabolic effect? I mean, the parabolic. Do you see the parabolic relationship in here? How it's like...
I can see it curving a little bit.
You see that a little bit? So when I go over here to R, and I insert the term that will allow me to create a bendy line that does that, the term came out significant in the model. And actually, that term is the most significant. The parabolic relationship is more significant than the linear relationship. Because if you look at the data right here, there's not much of a linear relationship to it. Like if you put a flat line, that flat line really doesn't do well, right? You see how a flat line doesn't really, I mean, it's like a nothing, right? But if I put in a bendy line right here, the bendy line looks more significant. Like I could draw a bendy line that would do a better job explaining this, right?
Yeah.
So the polynomial term is actually more significant. Here's my polynomial term right here. The second degree polynomial term is more significant than the linear term is in the model. The linear term is still significant, but if you notice, the effect of the coefficient of the polynomial term is higher and thus more significant. It has double, almost literally, double the t-statistic, which is a way smaller p-value. These curves bend like this. They don't go like flat out. So I was able to, and I just want to reiterate again, when I looked at this, I was able to see the bend in the data, and I'd say, oh, that looks like there's some sort of parabolic relationship. When you look at this, you say, oh, that looks like there's some sort of linear relationship to me. Do you see how you see that all immediately? Oh, there's some linear relationship. There's some parabolic relationship. Oh, there's like no relationship. I mean, if I do that right there, I'm not going to find anything really. I'm not going to find significant linear or significant I mean, maybe I will due to pure chance or just there's something small, but yeah. Did that help with it a little bit? How I'm able to see a parabolic relationship and then, run it and check it?
Yeah, and like if you looked between average humidity and demand, like on the almost on the bottom left, but like one up.
Are you talking about? So you're talking about go to average humidity and demand right here? I'm sorry.
No, I go on the bottom left, but one square up.
Okay, let me see. Bottom left, one square up, right?
One square. Yeah, and that's kind of a parabolic relationship as well, right?
Yeah, and this should be just this graph flipped. It's hard to see sometimes, but this should be the graph flipped around. I'm trying to make sense of it. Yeah, because you can see the parabolic in here, right? Like this.
Mm-hmm.
And just take, that'd be right. What you have to do is you actually have to take it and mirror image it. If you were to drop this like this, like if you take this whole block and flip it like this, you see what I'm saying? Like just turn it counterclockwise 90 degrees, right? And then mirror image it. Do you see these points right here? If you drop it, it's going to be over here, but if you mirror image it, it goes to the right. That's those points right there. Do you see this like peak to the mountain? If you drop it, that goes on top, and that's the peak to the mountain. This and this are the same graph because it's average humidity demand, and over here it's average humidity demand. It's just oriented differently. So it's the same. It's just the same visualization, oriented differently.
So in your in your output in R, I know we're not going to have like R on the test, but when you have output in R,
yeah,
you're looking at the poly.
Do what now?
Can you pull up R real quick?
Sure. Idle.
So for your intercepts right here, you have the poly, your second term. So that first term, that's your linear because it's to the first term, right?
Yeah. It's just telling you like the way this is read is just as the first. This is average humidity. Like if I were to just have average humidity in the model, there might be a way for me to write this that. Let me do this. Let me subtract out. I think I can write this in such a way that it's gonna look a little nicer because I don't like that it says that. Let me subtract out poly 1 and then let me add in. I think it might go mad at me. We'll see if it likes what I do here. Did I spell it right? Okay, let's call this something different. Let's call this dude. I have too much fun with this stuff. Oh, I didn't run it yet, so there you go. I knew it when I was hitting it. I felt it. I was like, I didn't run that. Okay, so here's my dude versus other model, and look at it didn't jump it out. It's not jumping it out. I wanted to just have average humidity. Maybe if I run average humidity first, I don't know why it didn't subtract out that. Oh, then I'm going to have to add it otherwise. Okay, let me try to run this first. Nope, that's not where it goes. Okay, delete that plus. Let's see if this will work. Because I think this will look nicer. Let me call dude that. It's a messy model. All right, here we go. Oh, good. Check this out. Now when you see this proves the point that average humidity to the first right here is just our average humidity term because then it wouldn't let me add it, which actually that was proven in the previous one too. But when it tries to add that into the polynomial, it's like, oh, wait, that's already in the model. And that's why we get the NA because it's like, no, I can't add it in twice. It's already in there. So that is the first order term in the model. It's just average humidity. Like this right here is this.
So we can think of the orders as just whatever power it's being raised to, right?
Yes.
Okay.
That's how it. That's exactly what it is.
All right, I think that's about all the questions I have.
Cool. Yeah. Good questions, guys. I'm going to continue writing the test and sleep.
Yeah, thanks for doing this.
Oh, anytime, guys. We'll end this. Lots of great questions. Really appreciate it. I've got a few notes about what I write there. I think, oh yeah, that's what I'm going to put on. I got to make sure, I want there to be everything we covered. I want it to be very comprehensive. I think people will be all right tomorrow. Good seeing you guys. We'll end the meeting, and I appreciate you guys coming. See you guys later.
Appreciate you.
Anytime. See you, Chris. See you, Josh.